In the previous video, I discussed how you can use these rice tables in order to calculate for your unknown K values. Luckily for us, we can also use these rice tables in order to solve for unknown equilibrium concentrations, unknown really anything. And so, you can only do that though is if you are given the actual equilibrium constant. And so here I'm telling you the fact that I have a chemical reaction of HA in an equilibrium relationship with H plus and A minus. And so initially we have 0.5 molarity of this HA. And so very similar to the last ones and similar to like just life in general. Before you start this chemical reaction, initially you don't have any product. And so initially again, you have 0 for both of these H plus and A minus when it comes to the concentrations because they don't exist yet. So for change, similar to the previous problem, using that unknown value of x and using our balanced chemical equation, we know for every one of these HA that disappears, one H plus is going to appear and one A minus is going to appear. And so we can write that out the same way, illustrating the same thing as minus x for our HA, and then plus x for our H plus, and plus x for our A minus. And so when it comes to actually equilibrium, still kind of going to the same deal here. You're going to add your initial plus your change. And so your equilibrium for this is going to be your 0.5 molarity minus x. Here you're still going to be looking at x and x. And so, unfortunately, unlike the last problem, you have a bunch of x's here. I don't give you an equilibrium concentration to actually help you solve for x yet. And so there are a few extra additional steps that you have to kind of take here. And so when you kind of go through, and again, the next step here, if you're completely stuck, is always kind of go back to the quotient. And so the quotient here is still going to be your products, H plus times A minus over your reactant of HA. And so, even though we don't have numbers here, we can still kind of rewrite this out in some form, or your H plus is going to be x, your A minus is going to be x, or we can write on top x times x is x squared. On the bottom we have our HA is 0.5 molarity minus x, so we still have to keep that in that form. So even if you love math, not too sure of too many people who like the quadratic equation. And so if we have to go through and do this, the problem the way it's set up, you have to use the quadratic equation in order to get things straight here. But there is an assumption that we can potentially make in order to make our lives a little bit easier. And so one thing that we have to kind of assume whenever we look at this Kc value here is that this is not really favorable in the forward direction. What I mean by that is even though I write HA gives you H plus and A minus, this very small equilibrium constant states the fact that it is not very favorable for these reactants to become products. And so if this happens, it will happen, it's going to happen at a very small extent. And so even though I write out this problem, there's only going to be very small amounts of H plus and A minus actually produced from this chemical reaction, given that this Kc is relatively small. Now, if it were like 400, then yes, you would go to nearly completion. But here, you have 2.0 times 10 to the negative 5. That is a relatively small number. And so, one way to just double check and make sure you're not going to completely screw up your math later on is to use, there's a few equations depending on, like the book has a different equation than what I'm about to tell you. But if you kind of go through and use this equation of your initial concentration of, again, this situation we're talking about HA. So HA initial over, over your Kc. In this case, again, Kc is going to be 2.0 times 10 to the negative 5. So if we write this out, we have 0.5 molarity over 2.0 times 10 to the negative 5. And so for this one, I end up getting a crazy number of about 25,000. And so, general rule of thumb is if this number, and again I'm talking about the initial concentration of whatever you're looking at divided by the equilibrium constant, if this number is greater than 400, then you can safely assume that this stuff is not going to change too much. And what I mean by that is this 0.5 minus x, this x is so tiny that it's not going to have a huge dramatic effect on this initial concentration of 0.5. And so because of that, we can again use a safe assumption and get rid of this 0.5 minus x and replace it with just 0.5. Because again, assuming that that number is so negligible that this is not going to be an appreciable amount of stuff leaving it, we can assume that our equilibrium concentration is 0.5 because it hasn't changed too much from the initial concentration we started with. And so, if we do all of that, then our math becomes a little bit less complicated. And so here, if we have our x squared equals our 0.5, we can replace this with our 2.0. And so, let me get to my other side of my board here, sorry. And so we would end up with our 2.0 times 10 to the negative 5 equals our x squared over 0.5 molarity. And so once we go from there, in order to isolate things, we'd have to take the square root, again, just isolating x on one side, of our 2.0 times 10 to the negative 5, and molarity, times our 0.5 molarity. And so solving for this, I end up getting x is equal to 3.2 times 10 to the negative 3 molarity. And so we kind of go through and look at this whole concept. And again, this 3.2 times 10 to the negative 3 is relatively tiny when it comes to this 0.5. And so in order to solve for the very last thing, what we're actually looking for is these equilibrium concentrations. We know that our equilibrium concentration for our x and our x are going to be 3.2 times 10 to the negative 3 molarity. And this is 3.2 times 10 to the negative 3 molarity. And then we know this is 0.5 because, again, it doesn't change too much, but just to double check. And so if we have our 0.5 molarity minus our 3.2 times 10 to the negative 3, I end up getting 0.4968 molarity, and by any appreciable amount, this will still be rounded to 0.5 molarity, which is still relatively about the same of the initial concentration.